0.00 million becquerels per hour, and we have evaluated 10.0 million becquerels per hour. As for Unit 2, the reactor building itself was not damaged by the hydrogen explosion. However, because the blowout is open, we assumed that the radioactive materials which are produced in the reactor building is being discharged through this blowout panel into the atmosphere. Therefore, for the monitoring of Unit 2, we set a dust sampler at this blowout panel and monitor the discharge amount per the dust concentration and flow rate. Concerning the monitoring method, the dust sampler is set by suspending it at almost the center of the opening where it can collect radioactive materials. The dust concentration is approximately 1.8 to 1 times the fifth power of 10, and the airflow of the blow panel is 30 cubic meters per second. Therefore, the discharge amount for every hour is approximately 4 million becquerels, and the evaluation result for Unit 2 is 10 million becquerels per hour, which is rounded off. On the other hand, we are also measuring at the output of the primary containment vessel gas management system. Because the flow rate itself is very small, the discharge amount is also small, approximately 1,000 becquerels per hour. The value of cesium is above, and noble gas was found. The value is 9.5 times the second power of 10, mainly caused by krypton 85, and there is a possibility that the accumulated krypton from the incident has been inhaled. The discharge amount is 13.7 becquerels per hour. So we announced 14 billion becquerels per hour last week. Because there is no building cover for Unit 3, so as shown in the photo, we hung a dust sampler at the top of the reactor building by using a crawler crane and conducted the dust sampling as near to the top as possible. Basically the same as Unit 1, we conducted the sampling at 1 right above the reactor well and 2 right above the machine hatch, and evaluate the discharge amount of radioactive materials from the reactor building by adding these two values. The evaluation function for 1 above the reactor building is the dust concentration times 0.58 square meters per hour of the assumed steam generation amount. This amount is ideal considering that it is produced from the cooling water by the current water flow rate and decay heat. But actually, it is a little more. The evaluated amount from these conditions is 19 million becquerels per hour. And regarding the number 2 machine hatch, it is evaluated at 15 million becquerels per hour by multiplying the dust concentration measured by the crawler crane and the wind flow at the machine hatch opening. By summarizing these values, the evaluation results for Unit 3 is 34 million becquerels per hour, or 40 becquerels per hour. In consideration of the above, page 10 shows the evaluation results for Units 1 to 3, and by summarizing each rounded value, we currently assume that 60 million becquerels per hour is the amount of radioactivity from the reactor buildings. And for the comparison, the evaluation result on the ocean where no influence of resuspension from the ground is 20 million becquerels per hour. There is a note, but basically the method is the same as the ground. That is, the actual amount of radioactivity is measured by a diffusion function. Page 13 shows the method of evaluation on the ocean. We conduct sampling by installing a sampling facility on this type of ship. Furthermore, the backdrop is dark because most of the sampling is conducted at night. We chose to conduct sampling at night because this is when the west wind blows from the direction of the reactor building towards the ocean. The results were 15 million becquerels per hour, or rounded off to 20 becquerels per hour. Return to page 10. Combining these two pieces of data at the ocean, it is assumed that the wind direction has a significant impact. Our current evaluation result is from the measurement amount above the reactor buildings. Therefore, the result is 60 becquerels per hour. By using this 60 million becquerels per hour, the evaluation result for the exposure dose at the site boundary is 0.1 millisieverts per year. We will explain this in the attachment, and page 2 shows the evaluation exposure dose by the discharge amount assumed from the current radioactivity concentration. If the discharge amount of radioactivity is obtained, the exposure dose at the site boundary is assumed by using explanation 2 at the bottom. Some evaluation functions are in line, but once the point of measurement, that is, the positional relationship between the site boundary and the building becomes clear, then the exposure dose is defined unambiguously the same as the previous one. Going back to the document, the result through such an evaluation is 0.1 millisieverts per year. In terms of the management and control of radioactive materials being used for the decision of the cold shutdown, because the target is under 1 millisieverts per hour at the site boundary, we assume that the management and control is achieved on the side of the discharging radioactive amount. Regarding the noble gas of Unit 2, different from cesium, we evaluate the radioactive amount from krypton to be 14 billion becquerels per hour. The influence of the gamma ray emitted by this noble gas is quite smaller than cesium. That means it is only external exposure by passing radioactive materials. Therefore, in light of the diffusion, the radiation dose at the site boundary is 0.00012 millisieverts. Basically the same as the previous one. We assume that it shifts to the safe side per the evaluation of cesium 134 and 137. Finally, we constantly conduct an evaluation of the discharge exposure dose of the units 1 to 3 reactor buildings. And currently, the primary containment vessel gas management system is only for Unit 2. But we will also install it for Units 1 and 3 and conduct direct monitoring in the primary containment vessel. As for the summary, the actual method of such discharge management will change slightly. We will continue to manage appropriately according to the field conditions. We apologize for the long presentation. This concludes our explanation of the evaluation method for the current discharge amount of radioactive materials from the reactor buildings.